Yes, sir. We can start, sir.
Can I start?
1 minute, sir.
Yeah.
Good afternoon, everybody. We have with us a distinguished scientist, Dr. Reji Philip, who is the professor at Common Research Institute. Welcome to you, sir. On behalf of everybody, welcome to you for this.
Thank you so much.
In fact, KSTA is very grateful to you for accepting our invitation to deliver this talk on Nobel Prize on Physics 2023. I also welcome all the attendees who have joined from different parts of Karnataka, both on Cisco WebEx and also YouTube platform. Before beginning the talk, let me give a brief overview of the achievements of Dr. Reji Philip, sir. Dr. Philip is a senior professor and currently the head of the Light and Matter Physics group of the very esteemed and prestigious Raman Research Institute, Bangalore. After obtaining his PhD degree from CUC at QSAT, Cochin, he worked as a postdoctoral fellow at the University of Regensburg, Germany, and as a visiting scientist at TFR, Mumbai, before joining RRI as a faculty member. Dr. Philip's research interests include laser-produced plasma, ultra-fast spectroscopy, nanostructuring using ultra-fast laser pulses, and non-linear optical behavior of novel materials. He has published more than 200 research papers in peer-reviewed national and international journals of repute. He holds 2 patents to his credit and has co-authored 3 book chapters. He has mentored several PhD students, postdocs, and visiting project students. Dr. Philip is a reviewer to several international journals from reputed publishers like the American Institute of Physics, American Chemical Society, Optical Society of America, Royal Society of Chemistry, Springer and Elsevier. He has been in the organizing committee of several national and international conferences and has held visiting scientist position at the University of Massachusetts, Boston, and the University of Central Florida. Dr. Philip has given more than 150 invited talks, keynote addresses, plenary talks in national and international conferences. So, Professor will be speaking on the works of 3 Nobel laureates in physics, especially on experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. So, with this very brief background, I request Dr. Philip sir to take over and deliver his talk. Now, over to you, sir. Once again, welcome to you.
Thank you so much, sir, for the very kind words of introduction. And I thank KSTA for this opportunity to talk to you about the Physics Nobel Prize 2023. Is this moving? I have a problem.
No, sir. No, sir. Still, it's in the first slide, sir. Yes, sir. No
now?
change. No, sir. No change.
Now it came, correct?
Yes,
Yeah.
Yes, sir.
Okay, thank you. I don't know why it was stuck for a moment. Yeah. So the Physics Nobel 2023 was awarded for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. The our laureates this year are Ferenc Krauss, Anne Lullier, and Pierre Agostini. So in this talk, we will see what is it that they have done for receiving this Nobel Prize. Again, it seems to be stuck. Okay, I think if I use my mouse, it works. All right. Okay, so basically, 1 attosecond is 10 to the power minus 18 seconds. And why do we really want to generate light pulses of such extremely short duration? So the motivation is the following. So if you can see here that this video doesn't seem to be working, but actually originally in this video, this electron would be going around the nucleus. And if you take the hydrogen atom for the n is equal to 1 orbit, we can calculate the orbit time, or the time it takes for the electron in a classical picture to complete one trip around the nucleus is as short as 152 attoseconds. So this is a very, very short time. And so therefore, and this is what you have on the left side is the quantum mechanical picture, where we do not really look at electrons as single points or anything. Of course, we know that it's a wave. The electron is basically a wave, and that exists around the in the atom around the nucleus. So we have a wave function and all that to find out the probability of the electron being at any point in space at any given time. Anyway, in the classical picture, this is how things are, and we can still do experiments whereby we can in fact observe things at very short time scales. Like for example, the action of valence electrons, the transition of electrons from, let's say, from one state to another. So all those things happen in attosecond time scales. Now, if you look at historically how we have looked at times and what are the things that happen in short time scales. So if you have a stopwatch, then we can say that rather reasonably, you can have a resolution of 1 second in your measurement. This is a kind of hand stopwatch that we have. So, and there are of course stopwatches which have better resolution than this. However, this is approximately how a stopwatch, what kind of resolution can give us. Now going to a camera shutter. So the fastest camera shutter can have milliseconds resolution. So when we go to chemical reactions, these happen at much shorter time scales, like in microseconds, and very fast electronic devices work in nanoseconds, and the vibrations of molecules, molecular vibrations happen in picoseconds. Photosynthesis is very fast. It happens in femtoseconds actually. And the motion of electrons in atoms and molecules, it happens at even a shorter time, like attoseconds. So this is why when you want to measure something in the time domain, you need to have something of a clock which has a better resolution. Otherwise, you cannot measure it. So this is the reason why we are trying to make shorter and shorter pulses by which we can measure the events that happen at very short time scales. Now, to understand this better, it is necessary that we look at the history of maser and not of the laser actually. Then we will look at how we make short pulses. So Q switching is the technique for making nanosecond laser pulses. Mod locking is another technique by which we can make picosecond and femtosecond pulses. And when it comes to making attosecond pulses, we have to make use of a technique known as high harmonic generation. And high harmonic generation will normally give us a train of attosecond pulses, that is several attosecond pulses which go one after the other. Then, however, for some experiments, we really need isolated attosecond pulses. That means just one attosecond pulse. So how to make them? And then what are the applications of these pulses? That's what we will see in this talk. All right. So this is how you make a laser. First of all, in your system, you have to have a gain medium, some kind of an optical gain medium. So you have to have population inversion there. And if you have inverted the population in your system, that is the number of atoms or molecules which exist at a higher energy state should be more than the number of atoms or molecules which exist at the ground state. That is what is meant by population inversion. So we can invert the population by means of optical pumping, electrical pumping, and methods like that. Once you have inverted the population, we will see that stimulated emission, which happens in the system, is increased. So it becomes enhanced, and stimulated emission can be pretty strong so that there can be amplification in the system if you have a cavity. So this is the reason why if you look at a laser, it always has, most lasers, all the regular kind of lasers have an optical cavity there, which means there will be two mirrors at the end of the laser cavity, so that the stimulated photons will keep going back and forth, and in that process they will amplify, because they will generate more stimulated photons. So when you have a large number of such photons which appear by means of stimulated emission, they will have the same polarization, they'll have the same phase. So when you have something like that, that is called a laser, because it has coherence, it has monochromaticity also. So such optical beams are known as lasers. So that is what you see here in this picture. The first system which was based on stimulated emission was not really a laser, it was the maser. The maser is the full form of this acronym is microwave amplification by stimulated emission of radiation. This can be considered as the precursor to the laser, and these are used as timekeeping devices in atomic clocks and as extremely low noise microwave amplifiers in radio telescopes and deep space spacecraft communication ground stations. So that's what masers are used for. And these two people, they discovered the maser. This is Arthur Shallow and Charles Towns. And they were also awarded the Nobel Prize for this discovery. So this is Charles Towns with the ammonia maser, which he built. In fact, many years back, Towns was in Bangalore. I mean, at least I remember him coming here once. This was way back in year 2000 or 2001. And he gave a talk in the IAC campus that time. I remember attending this talk. So now in 1957, after making the maser, they start a serious study. Both of them are working at Bell Labs in New Jersey at that time. And they want to extend the principle of the maser to the infrared region. So that means infrared is optical region, coming very close to the visible spectral region. So, and later they actually started concentrating on maser action in the visible spectral region. So they used to call this the optical maser. However, it was not Towns or Shallow who actually demonstrated the very first laser. It was done by Theodore Maiman, who was working in Hughes Research Labs in California at that time. And what he discovered is called a ruby laser, because he used the ruby crystal as the working medium or the optical medium in the laser that he built. This is a picture of the laser that he built. We can see the ruby laser rod in here, and there's a helical flash lamp here. So this is the kind of flash lamp which was used in cameras in those days. So this is here, we can see Maiman with his flash lamp and the small laser cavity. So the way it worked was, so this crystal where chromium is actually doped, Cr3 plus is doped in Al2O3. That is what ruby is. The absorption happens in the green and in the blue regions for this material, and the emission happens in the red region. So this is a metastable state, and from this metastable state, laser action happens. So this is called a 3-level system, basically. This is together, this is considered as one level. This is the second level, and the ground state is the third level. And once lasers were invented, there were a lot of modifications, developments in this area. And the first laser by Maiman was actually a very long laser pulse by today's standards. It sort of gave the almost in fact, a little bit less pulse width than the pulse width of the flash lamp, which pumped it. So it was like 100 microseconds. So that was a kind of laser pulse width we obtained from Maimann's Ruby laser. However, very fast, the Q switching technique was discovered by Hellwarth, and then the pulse width could be brought down to 100 nanoseconds. And then comes the technique of mode locking, close to I think in 1967 or so. By the mode locking technique, the laser pulse width could be further reduced to 100 picoseconds. Then different materials are tried, and then the pulse width is coming down again, like it's coming down to almost 100 femtoseconds. And at that time, Donna Strickland and Gerard Mauro, they discovered the chirped pulse amplification technique, the CPA technique, for which both were awarded the Nobel Prize about 5 years back. Then after that, the another technique for mode locking, which is called curl-length mode locking, is discovered, which is an efficient way of doing it. And then it is after that the real studies in attosecond pulses started appearing. So in 1987, so in this region, if you look, in 1987, Anne Lullier fires a laser at a noble gas to produce, and she finds that overtones of light are produced. So later we started calling it high harmonics, but at that time these were called overtones of light. And then they started exploring the mechanism behind these overtones. And in 1994, Agostini begins to develop a pulse measurement technique, which was later known as RABBIT. We will see that along the way. And in 2001, Agostini produces a train of 250 attosecond pulses. So this is the first step into the attosecond domain. And then around the same time, Ferenc Krauss isolates a single 650 attosecond pulse. And by the 2000s, the attosecond pulses are being used to explore the motion of electrons in various materials. And in 2023, the three of them are awarded the Nobel Prize in physics. In fact, there are a few others also who worked in this field and contributed a lot to attosecond science. But then, of course, everybody cannot get a Nobel Prize, and the real pioneers, some of them actually get the Nobel Prize. Now, how short is actually the attosecond pulse? To know this is called a nomogram. So if you look at this nomogram, this one is actually for femtosecond pulses. So this one is a bit old. Maybe there are already such pictures now in the internet. This I took from the internet. So maybe they are there now for the attosecond pulses also. But anyway, I will talk about this and I'll just extend this to the attosecond domain. So now here on the right side at the edge, you can see the age of the universe. Okay, how many seconds it is? It is more than 10 to the power 16 seconds, as you can see. And at the center, you have a time duration of 1 minute. Now, if you go the same distance towards the left, you can see a 10 femtosecond light pulse. So here, from this, what we understand is that how large is the age of the universe in comparison to just 1 minute? That much you have to go back in time, not go back, but that much shorter you have to go down in time to reach a 10 femtosecond light pulse. So now you can understand how short it is, extremely short. And we are talking about attosecond time domains, which is like now the shortest we have, I believe, is something like 150 attoseconds, which means it's about 100 times smaller than a 10 femtosecond light pulse. Okay, so we will have a brief look at Q switching. In Q switching, we modulate the cavity Q factor in time. So, and that's how we generate nanosecond pulses. So just look at this picture. So I'm showing part of a laser cavity. So there are laser photons here. Imagine laser photons coming, the stimulated emission photons coming from the left side and then moving through the polarizer and then through the focal cell and coming back because of reflection at the rear mirror. So the polarizer makes the beam polarized in one particular plane, and the focal cell is something which causes birefringence to the system. It is an electro-optic crystal, actually, the focal cell, the Focal's effect. So what happens here is if a voltage is applied to it, it will introduce a phase, a rotation of the polarization of the beam as the beam passes through. So therefore, the polarization rotates by 45 degrees when it goes towards the right side, and when it traverses the focal cell once again, it again goes through another 45 degrees change in the polarization angle. So together 45 plus 45 makes 90 degrees, and now the polarizer will not allow the beam to go back because the polarizer allows only, let us say, vertical polarization. Now it has become horizontal polarization because of the passage through the focal cell. So therefore it is blocked there. So what is done is, in a typical laser that produces nanosecond pulses, because this is electrically induced, you switch on the focal cell voltage. It is typically something like 3 kilovolt, 4 kilovolt and all that. So you keep the focal cell voltage on and then apply the pumping, that is optical pumping or electrical pumping, whatever. So the pumping is applied, there is population inversion, the medium gets inverted, that is, it reaches the maximum inversion point, and then only the voltage in the focal cell is switched off. When you switch off the focal cell voltage, it becomes like just a piece of glass. So it doesn't introduce any polarization change after that. So therefore, immediately the cavity becomes open for the photons to pass through. So until this time it was blocked. So the block is removed, it suddenly becomes open, but now the situation is that the population inversion in the system is so large that you get a very strong laser pulse out of it. One flash of light, which is much more powerful than the flash of light which you would have got if you did not have a focal cell there. So this is called Q switching, and we can make nanosecond laser pulses this way. Almost all nanosecond laser pulses work in this fashion by using a focal cell. Now, suppose you want to go a little shorter in time, like let's say we want to make picosecond and femtosecond laser pulses. Now we have to depend on another technique. This is called mode loop. So the way it works is as follows. There are longitudinal modes. I mean, take any cavity for that matter. It could be an acoustic cavity, for instance, a pipe. Okay, so anything like that, any cavity has resonance frequencies in that. The cavity is like a tuning fork, has a resonance frequency for it. Now, if you take an optical cavity, for the optical cavity, which is bounded by two mirrors, there are longitudinal modes, frequency modes, which can be sustained by the cavity. And there are a large number of them. And these longitudinal modes are separated by the frequency interval delta nu is equal to c by 2l. So where L is the length of the cavity, c is the velocity of light. Now, even though a cavity can sustain a very large number of such, an infinite number of such modes, frequency modes, only those frequency modes which come under the gain profile of the laser medium will be there. So what this means is, now I have, let us imagine I have a laser that produces red light. Okay, something like ruby, for example. So as we know, the laser beam is it's monochromatic. So therefore, the frequency bandwidth of the laser beam is very, very short, very, very small. In that, therefore, even though ideally the cavity can support all these frequency modes, they won't be there. Only very sharp red light, because very monochromatic red light. Therefore, you will have a few frequency modes in that because they're very close to each other. You will have a few. Now we will see how many are actually there in this example. So how many frequency modes are there in an optical cavity? So let us see, let us compare two different cavities, two different media, and then compare. Take the first example. This is for the helium neon laser. So all of us know the helium neon laser. And consider a cavity of length 30 centimeter. For L is equal to 30 centimeter, delta nu is equal to C by 2L is equal to 0.5 gigahertz. Now, the bandwidth of the helium neon laser light, the emitting line, including Doppler broadening, is only 1.5 gigahertz. So this translates to 0.002 nanometer width at 633 nanometer. Therefore, within this 1.5 gigahertz bandwidth, if you have a frequency separation of 0.5 gigahertz between adjacent frequency modes, then you can have only 3 lasing modes in that. That is 1.5 by 0.5 gives you only 3 frequency modes in your cavity for the helium neon laser. Now take the example of the titanium sapphire laser. So instead of helium neon, you have a titanium sapphire rod as your laser medium there. Again, the cavity length is the same. So therefore, delta nu is equal to 0.5 gigahertz. But the bandwidth for titanium sapphire is very large because it emits like a dye molecule. It's very broad from 700 nanometer to 1000 nanometer. Titanium sapphire rod can emit. This bandwidth is about 128 terahertz, and therefore, if you divide that by 0.5, you see that you have 250,000 frequency modes in your cavity. So that is the difference between a helium neon laser and a titanium sapphire laser. We also have to say that, okay, I'll come to that a bit later. It's about monochromaticity. So the point that we have to remember here is that for a titanium sapphire laser, which has a large bandwidth of emission, the number of frequency modes you have in the cavity is very, very large. Now the question is, the phases of each of those frequency modes, they're all oscillating randomly. So there is no connection, no proper connection or correlation between the phases of each one of those frequency modes. Now, is there a way in which you can synchronize these phases? And if you synchronize like that, what will happen? So that is the picture you see here. Here you can see each longitudinal cavity mode like that. Each frequency is different, so the wavelength also is a bit different. Now, when waves like that travel together, if they are synchronized in phase, then you can see that this is the point where they all synchronize in phase. I mean, at that particular point, there is constructive interference between all the waves. And when that happens, you can see that the amplitude is really large. But if you go either way, this way or this way, so you have time here on the x-axis, so you can go only this way actually. So then you see that they are going off phase. So therefore, when one is going up, the other is going down. So after interference, you really are not really going to get anything substantial there. But after a while, you will get the same pulse again. So the pulse will repeat. That is what you see here. This is one pulse in the time domain. This is the second pulse. So like that, you will get a train of pulses when you have synchronized or locked the different phases of all the frequency modes. There are methods in which this locking can be achieved. Like, there are active methods, there are passive methods, and at a repetition rate of C by 2L, these pulses will come one after the other from the laser. So this is called a mode locked laser. And the advantage here is that the pulse width of each of these pulses, so each of these is one pulse like that. The width of each of these pulses will be inversely proportional to the number of frequency modes you have. So therefore, as we have seen in the case of the titanium sapphire crystal, because we have more than 250,000 modes in that, the pulse width will be extremely short. So this is equivalent to making the statement which we know that when you have a large spread in the frequency domain, you will have a very short pulse in the time domain. For example, if you take the Fourier transform of a very short pulse in time, let's say a delta function in time, if you take the Fourier transform, what you see in the spectral domain is white noise. That is, it's very, very broad. So that is the same principle which is applicable here also. Now, let us see what I see, what I show you here is an actual measurement in our laboratory, because we have 100 femtosecond laser pulses. We have a femtosecond laser system. It produces sometimes 100, depending on the tweaking and tuning that you do. You can get 90 femtosecond also. So this is the pulse train of 90 femtosecond. Each of these pulses is a 90 femtosecond wide laser pulse. Now, one might wonder, can you really see such an extremely short laser pulse in a normal lab oscilloscope? This is a normal lab oscilloscope. It's not really very high frequency or very fast device, but even then, you can see the separation between adjacent pulses very clearly, because these femtosecond laser pulses generated by a TISAF laser at the repetition rate of 82 megahertz, the pulses at 82 megahertz, the pulses are separated in time by about 13 nanoseconds. So this is that 13 nanoseconds. No oscilloscope works as fast as 90 or 100 femtoseconds. So therefore, if you try to measure the width here, it is truly, this is only 90 or 100 femtoseconds. If you measure it here, what you will see will be something which is broader than that, because the rise time of the oscilloscope is given by 0.45 divided by its bandwidth, which is 100 megahertz. So that is 4.5 nanoseconds. This oscilloscope cannot measure anything that is less than 4.5 nanoseconds. However, the separation is 13 nanoseconds. So therefore, it will measure the separation. It will show the pulse also. But if you try to measure this, you will never see 100 femtoseconds. It will be a much larger value. That is the limitation of the oscilloscope. So the question is, how do you measure femtosecond pulses? There are other techniques like autocorrelation techniques which you have to use. You can never measure the width of a femtosecond pulse in any electronic device. So this was the 2018 Nobel Prize in Physics for, as I mentioned, Gerard Mourou and Donna Strickland from the University of Rochester for inventing the technique called chirped pulse amplification, or in short CPA, of femtosecond laser pulses. So this way they could actually increase the power of femtosecond laser pulses to much larger values. I mean, like from nanojoules to millijoules. So this was a huge advantage in terms of application. So that's why they received the Nobel Prize in 2018 for this discovery. Okay, so that much about femtosecond laser systems. We have a femtosecond barrier. Can we go by using the same technique of mode locking? Is it possible for us to go down and obtain attosecond pulses? Actually, you cannot. The reason for this is that the best material we have found so far for making a very short pulse is the titanium sapphire crystal. And the qualification for being a material that can produce a very short pulse is that it should emit in a large spectral range. The titanium sapphire crystal has an emission bandwidth of about 100 terahertz. So that's, as we have seen earlier, 700 to 1000 nanometer approximately. It emits in all that region. And therefore, it can support a mode locked laser pulse, transform limited pulse of 4.5 femtoseconds. Little bit less it can go, but certainly not less than 3 femtoseconds or something. That is the limit. And unfortunately, no other material has been found which has a larger bandwidth with high gain in the visible spectral region. So therefore, it is not really possible. So the femtosecond barrier, this is called the femtosecond barrier. This can be beaten for creating attosecond light pulses only by finding a way to generate a series of periodically spaced frequencies which cover a much larger spectral range. So that is basically what we need. A larger spectral range should be covered in the emission. Then you can compress. It is possible to, theoretically, it is possible to compress such a pulse to the attosecond. Now, two methods have been found to be useful for this. The first method is called high harmonic generation, or in short, HHG in gases. And the second method is cascaded stimulated Raman scattering. Now, stimulated Raman scattering is not really used much for this. I don't know whether this video is playing. Doesn't play. Anyway, it doesn't matter. I will explain. So let us see what is the high harmonic generation process. Now, this needs to be understood to understand almost everything that comes later. So consider an electronic system. Let's say take the case of an atom or a molecule and think about the valence electron at the outermost orbit. Now, the valence electrons are the electrons which are most loosely bound to the nucleus because they are farther away from the nucleus. And we have to apply sufficient energy. I mean, the ionization energy is there. So if you apply the appropriate ionization energy, then you can ionize a valence electron. Now, what happens here is normally, if you want to ionize many atoms in particular, then you have to apply photons at a high energy. Like, this means you have to go to the ultraviolet region. So materials mostly can be ionized by photons in the ultraviolet region. However, we can have phenomena like tunnel ionization, which work in a slightly different way without really applying ultraviolet photons to the system. For example, in this case, we use a titanium sapphire laser, which works at 800 nanometers. It is, of course, close to the infrared. And sometimes even in the infrared itself, like 1.06 microns for an Nd:YAG laser. So these kind of lasers can really be used for ionizing materials. This is known as multi-photon ionization. Now, we have multi-photon ionization. We also have tunnel ionization. The technique used for high harmonic and attosecond pulse generation, which follows from this, is to make use of tunnel ionization of an electron. So let us see what happens here. What we see here is the potential well of the nucleus, and the electron is here. So normally it is it's a potential well. It's like this, and the electron is somewhere in the boundary region here. Now this is the applied laser pulse. You can see that the laser pulse, this is the way the laser pulse amplitude changes because it is at 800 nanometers. So that is a wavelength. And the importance here is that the field amplitude is very high because it's a laser pulse. Therefore, the amplitude of the electric field associated with the electromagnetic radiation, which is the laser pulse, is large. And that electric field is capable of modifying the nuclear potential in the atom. So therefore, what happens is the nuclear potential, which can be considered flat in a picture like this, it gets tilted because of the application of the external laser pulse. So it can get tilted like this initially. Then after that, it changes direction because the amplitude here it is positive and here it is negative. So in a similar way, the potential seen by the electron here also changes. Now, when this happens, as you can see here, which was the wave function of the electron is now depicted like this, but it can now tunnel out of the nucleus, out of the atom this way, because the potential has been changed. And then it can come back. So we have three different steps here. So this is called a 3-step process. So the first step is ionization, which is tunnel ionization. It's just tunneling out, which is a quantum mechanical process. And then there is motion after ionization. The electron travels like that. And when the sign of the amplitude changes, that is from positive when it goes to negative, the electron comes back towards the original parent atom, and then it recombines with the atom. So you have strong field ionization, then the propagation of the electron, and then recombination of the electron. So when the electron comes back and recombines with the parent atom, it emits radiation. And that radiation is at very high frequency. So that is the high harmonic emission. So this is called the simple 3-step process. This is a semi-classical model. There is also a complete quantum mechanical model for this, but this is pretty understandable for anybody to see how this actually happens. In the original experiments, people used like, ND glass laser, that is 1053 nanometer. This is in the infrared. So by focusing 1 picosecond laser pulses from an ND glass laser to a Nobel gas target at intensities between 10 to the power 14 to 10 to the power 15 watts per centimeter square, harmonics up to the 29th in xenon, 57th harmonic in argon, and 135th harmonic in neon, they were measured by Lullier. So as you can see, in 1993, she made these measurements. So certainly a milestone in the history of short laser pulses. So, and these frequencies like, 29th harmonic, 57th harmonic, etc., they will lie in the soft X-ray regime or the extreme ultraviolet regime. So for soft X-rays, the wavelength is from 0.1 nanometer to 10 nanometer. And for XUV, the energy is like 120 eV to 10 eV. And the wavelengths are from 10 nanometer to 120 nanometer approximately. So that is where you get these overtones. So we can see here, Anne Lullier, she was the one who observed, as I said, multiple harmonic conversion of 1064 nanometer radiation in rare gases. So she also studied multi-photon ionization before that, high harmonic generation. And she also explained the plateau in high harmonics. So this is how people obtained the harmonics, the harmonic frequencies. Initially, there was a sharp decrease, and then after that, there was something like a plateau. Not exactly like this, but it is more or less a plateau for several harmonics, and then there is a cutoff. So Lullier explained the plateau, why this plateau comes. She explained that using the time-dependent Schrodinger equation, and she solved it using the single active electron approximation. And then she also contributed to the full quantum theory of the process along with Levenstein and Corkum. And she also explained something called photoionization discrepancy by considering OJ electrons or shake-up electrons in the system. So there are various contributions that Anne Lullier did to the study of high harmonic generation. She explained the process of high harmonic generation in this way. And I've taken these pictures from this paper by Nisoli, M. Nisoli et al., which is a very good review of the attosecond pulses, and the complete history and lot of details are given, lot of applications are given, everything is there. So it was shown that, as you can see here, the harmonic order, it extends from 25 to 55 in this case, and these appear at slightly different times. And this is the experimental measurement, and this is the theoretical prediction. And you can see that they are in reasonably good agreement. And this is how you measure it. You can see you can use a spectrometer for this measurement, the EUV spectrometer. And the energy was from 20 electron volt to about 100 electron volt in this case. And this is the plateau. You can see the plateau here. And this is how in time the attosecond pulses come out. So here you can see a pulse. This is one pulse. This is another pulse. So a train of pulses like the femtosecond pulses. So how does it work here? It is a bit different from the femtosecond process. What happens is the continuum component of the electron wave packet interferes with the component that remains bound to the parent ion. The continuum component means what came out, what tunneled out of the parent atom. So there is a part that remains with the parent atom. There is the other part that tunnels out and then comes back. The coherent overlap of these two components generates an electric dipole, and the center of mass of the total electron distribution oscillates back and forth as the continuum wave function propagates. This electric dipole acts as an atomic antenna, lasting just a small fraction of an optical cycle of the driving radiation, and that leads to high harmonic emission. So that is what happens. This is the lab of Anne Lullier, just a photograph from of her laboratory, and more details one can see in this website. Anne Lullier's Lund University. She works in the Lund University, and these are some of the PhD theses which has come out from her research group, and they are all very interesting works. Now coming to Pierre Agostini, he was the one who observed attosecond pulse generation from the high harmonics. So he was the first to do this in 2001, and the paper is published in Science. As you can see here, observation of a train of attosecond pulses from high harmonic generation. And before that, he had actually realized experimentally something called above threshold ionization. And not only finding a train of attosecond pulses from high harmonic generation, he also developed a technique called rabbit. So this is reconstruction of attosecond beating by interference of two photon transitions for measuring attosecond pulse widths. So as I told you earlier, it is one thing to make the attosecond pulses. It is equally demanding and difficult to measure the real pulse widths. So people had to invent new techniques for this. So what happens in rabbit is that the photoelectrons produced by the ionization of a target gas by the attosecond pulses are measured in the presence of a weak time delayed infrared laser field by something called F2F interference technique. So that's the way this is measured. So this is the experimental technique. As you can see here, I haven't really gone much into the experimental technique, what they use here, but this picture tells us everything. So this is the real measurement by this technique, and you can see that the width of these pulses is just 250 attoseconds. That it's very, very extremely short, and the gap between adjacent pulses is only 1.35 femtoseconds. So therefore, by the rabbit technique, they have been able to measure this extremely short pulse width. This is the lab of Agostini, one photo from the laboratory. Now coming to Ferenc Krauss, he also has a lot of contributions to the field of attosecond science. And in fact, one of my PhD students, he did postdoc in Sweden, in Umeå University, with a student of Ferenc Krauss. So we were all very happy to know that Ferenc Krauss actually got the Nobel Prize. So he developed the fuse cycle laser pulse laser, fuse cycle laser. He developed that, and he generated, of course, when I say he, that means his research group led by him, generation of a broad high harmonic spectrum generation of the first isolated attosecond light flashes. So this is important. Instead of having a pulse train, if you have a single isolated pulse, then you can do a lot of spectroscopy with that. So Ferenc Krauss did that, and measurement of the isolated attosecond pulses using cross correlation and attostreaking techniques. The extension of these techniques to attosecond metrology, the application of attosecond pulses to record electron dynamics in various systems, including biosamples. So these are the contributions of Ferenc Krauss in this area. So we will see how he generated isolated attosecond laser pulses, attosecond pulses. It is not really correct to say attosecond laser pulses because lasers are monochromatic, and traditionally lasers are monochromatic. Attosecond pulses are not monochromatic. This requires, if you want to isolate an attosecond pulse, it requires the shortest pump pulse. The shortest pump pulse would be, those pulses would be fuse cycle pulses. What do we mean by fuse cycle? What it means is, well, I mean, you have a certain wavelength for light. Now imagine one cycle is just like that. I mean, just one wave. What would be the time scale for just one wave to happen? So when we say wave, we always have multiple waves like that. Here, what happens is fuse cycle femtosecond pulses are just fuse cycle, as you can see here. 1, 2, 3, 4 maximum. So that is what it has. It doesn't have any higher number of waves in that. So what Ferenc Krauss did is that, and others also did, but he pioneered this work, is that he expanded the spectrum of femtosecond lasers even further by a technique called self-phase modulation in some gases. So what he did was he used hollow core fibers, and filled those fibers with HCF, that is, some gases, to get self-phase modulation. And the pulse spectrum was stretched by a nonlinear process there, and this added spectrum of the pulse allowed a better compression. So after compressing the pulse, it was only like about 3 femtoseconds. So this kind of a titanium sapphire laser he used, that is a modified titanium sapphire laser, which produces extremely short pulses like 3 femtoseconds, a little bit above that, was used for making high harmonics. So by doing that, he succeeded in making isolated attosecond pulses. Now, once you do that, again, you need to measure the pulse width of these pulses. And he used a technique called attosecond streak camera for that. Here what happens is the EUV pulse produces an electron wave packet by photoionization in the presence of an IR pulse, which is called a streaking pulse, which is weak enough not to ionize, but strong enough to impart substantial momentum to liberated photoelectrons. So the basically the measurement in the attosecond domain, the measurement is mostly based on the generation of photoelectrons. This is the lab of Ferenc Krauss in Garching in Germany. So people have tried different gases for making attosecond pulses, and some solids also have been investigated. So you can see here like neon, xenon, like that, mostly these gases are used, and the full width that have maximum values of the attosecond pulses, the energy, and then the pulse duration, as you can see here, is like 130 attoseconds, 155, 80, 67, like that. These could be trains, I mean, not necessarily isolated pulses. Pulse energy, as you can see here, is in the picojoule range, or at best it is nanojoule range. There is one report of microjoule, but people in the community believe that it's a wrong report because it's almost impossible at this point of time to get energies of that kind. So physics at the attosecond frontier. This paper appeared in 2001 after people actually started making attosecond pulses. So what this paper describes is what is the physics that we can do using attosecond pulses. When the laser was invented, people jokingly said, here is a solution looking for a problem. Because at first, nobody really understood what can we do with lasers. It was a fancy, very interesting beam. Everybody who sees a laser beam for the first time likes it because it's very different from the normal light that we are familiar with. However, in 1960, people had to think a while to find out what are the possibilities using lasers. But nowadays, we know there are lots and lots of applications for lasers. So like that, in the attosecond frontier, what would be the applications? Mostly in the attosecond domain, we will use these pulses, the attosecond pulses, for looking at extremely fast phenomena. So that would be the major application of attosecond light pulses, because we know we are reaching close to the quantum domain here. Like, the moment you are able to measure the motion of electrons, it's a very, very fundamental effect, fundamental process that happens in materials, in anything for that matter. Electrons move. So if you can track the motion of the electrons, you are at the threshold of, uncovering several quantum phenomena and also learning more about quantum mechanics. So all that is possible with attosecond laser, attosecond light pulses. One of the obvious applications would be transient absorption spectroscopy. So this is something people used to do with nanosecond pulses, with picosecond pulses and femtosecond pulses. So now we extend the process to attosecond domain also. So here we will be trying to look at, people have really looked at the excitation, de-excitation of electrons. So that kind of processes which occur in the attosecond domain have been looked at. Then charge migration in molecules. So this is also something that happens at extremely large speeds, very fast. So can you really follow? Can we chart out such processes? Is what is possible with attosecond pulses. Then, charge transfer, very similar mechanism, charge transfer in organic photovoltaic materials. So this is something everybody who works on photovoltaic materials, they also study the charge transfer phenomena. So we can really investigate these phenomena better if you have attosecond pulses at our disposal. So some of these are the applications, and many more applications will be there of attosecond pulses. Anything in time when you want to investigate with high resolution, the attosecond pulse is very, very useful. So here, this is a paper that appeared in 2023. I haven't really seen the paper. It's very recent, 3rd August 2023. Quantum optics meets attosecond science. So written by Professor Korkum and Dong Hyuko, maybe a student of his. So Korkum was in fact another person who many people thought will get the Nobel Prize for attosecond, but Korkum did not get it. He is actually he actually discussed the 3-step model, which we just saw. Anyway, he has written a very good paper where he is probably talking, of course, from the title, it indicates that he is talking about the applications of attosecond science in quantum optics. And we know that the quantum optics mission we have in our country, and many countries have taken this up, quantum devices. So until recently, we knew quantum mechanics as a completely theoretical paper, and people were not really talking about devices which you can make on the basis of quantum phenomena and quantum theory. But now in reality, there are devices which are coming out. So there are small devices in quantum optical domain. And when attosecond science meets quantum optics, we can expect a lot of exciting outputs from that. So these are the possibilities. And so what are the major challenges which we face as of now? There are a few, like the stability of the pump laser, because whenever you have something less than 5 femtosecond, it's actually a great challenge to really keep the laser pulse stable. So there are techniques called carrier envelope phase stabilization, which one has to adopt to. Then optimization of phase matching in the gas medium. This is important. Increasing the efficiency of high harmonics, generating non-jittery attosecond pulses. It should not be jitter in time. Attosecond pulse measurement, we have seen some techniques. Then XUV focusing. I mean, you have to focus the XUV is the high harmonic. So how to focus it? We cannot really use any lenses for this because lens will absorb. So therefore, we have to use mirrors for this purpose. Then minimize aberrations, maintain beam pointing stability. So all these things are practical challenges in the attosecond technology. Then even splitting a beam for pump probe experiments is a challenge. There are a few major attosecond research groups in the world. So of course, Max Planck Institute of Quantum Optics in Garching near Munich. Then MBI, Max Born Institute in Berlin. Imperial College, London. ICFO, France. Lund University, Umeå University in Sweden. King's College, London. TUVN, Ohio State University, Columbus, where Pierre Agostini is. UCF, Orlando. They do a lot of, in Creole, they do a lot of attosecond work. And Max Planck Center for Attosecond Science in Pohang. Extreme Light Infrastructure, it's a big facility. The attosecond light pulse source called ALPS in Szeged in Hungary. So this is part of, this is a European Union initiative. Now they are building an attosecond facility there. This LI is a very big facility with a lot of experimental facilities there. So I think I'm close to the end of this talk. Let me see. Yeah, that was the last slide. And thank you very much for your kind attention. And we can expect a lot of applications to come forth for attosecond science. And I'm pretty sure that in the coming years in our country also, there will be laboratories which will come up for doing attosecond science. And so we can wait for that. Thank you very much for the kind attention.
Sir, thank you very much for a very insightful and scholarly talk. On behalf of KSTA, we are very grateful to you. You talked about the works of Ferenc Krauss, then Dr. Anne Lullier, then Dr. Pierre Agostini, and their work, attosecond pulse technology applications and major challenges. And finally, you also told about the major research groups in different universities across the globe. It was really a very fantastic presentation, sir. Right from basics, you took us to applications and major challenges. On behalf of KSTA, we are very grateful to you for this very, very interesting presentation. Now we have with us Professor Kushal Das, sir, who is the director at PLE University. He is also a very reputed international scientist. Now, sir.
Hello, sir.
Thank you
for joining, and over to you for your words, comments.
Thank you very much, Dr. Ramesh. First of all, I really like to congratulate Professor for wonderful talk he has given. And I also apologize and say that I'm completely a layman in physics because I'm a medical professor in the Faculty of Medicine. So I belong to School of Medicine here. But it was so thrilling and interesting. And as a medical scientist and researcher, we often feel the knowledge of physics is extremely important. That is one thing I feel that our government, specifically Karnataka government, must emphasize for teaching purpose in the level of the PUC. Although we have it, we are better than many other states where the mathematics and physics given a priority, specifically mathematics. To understand physics, a good knowledge of mathematics is required. Very unfortunately, in my domain, including me, are weak in mathematics because we thought that we will not able to handle the physics and mathematics. So we like thinking. Then when I actually completed my medical and all the things, I not understood the importance of the medical for the physics purpose. I really got thrilled when I was doing postdoctoral fellowship at University College London under a great professor, John A.V. Morrison. So who was a Royal College surgeon also, and also happened to be a fellow of Royal Society. And his immense understanding of mathematics and physics, I really realized that I am a zero. I felt so ashamed of myself. So this is one way I feel the PUC student, whoever is listening now, listen from me as a medical person that mathematics and physics is a part of the medicine. If you really want to do it applied in clinical science, or you go for the basic science research, whatever it may be. Your talk was so relevant. Specifically, I was not knowing about the attoseconds. I heard this thing, but not at all understanding what is it. I never interfered. I never actually bothered to know it. But this thing make me thrill because it is connected with the laser. And as medical persons, we are often come across with the laser, not only to diagnostic purpose, but also in the surgical purpose. We have a laser guided knife by which we made the critical surgery. Specifically now the oncosurgery is under the knife of laser. So in this way, this is a well thought talk, and a veteran and a pioneer like you with an illustrious institution, Raman Research Institute, your background, I request all the students who are listening here, this is a fact. So don't omit anything, thinking that it is higher study or lower study. Nothing is like that. We still use Bohr equation, Laplace law for hemodynamics to movement of a blood to the vessels to develop the clot or protect the clot. And technology which physicists they do it with the support of the technologies actually must translate to the medical side people who are applying that this is a fundamental. So don't ignore that part. So this way, this talk is a very relevant. Specifically, the people of my medical science in my faculty or the life science students here who are taking the biological science, and many of them are thinking to join medicine, and or you'll be joining sir biological science, no need to study mathematics and physics. Absolutely, you are all wrong. Because in my life, I found how wrong it is when I actually finished my education degree-wise. Real practice world in the world research, when I entered, I found that I'm a big zero and such a drawback. So I request all the PUC students, this is your career building, don't ignore mathematics, don't ignore physics. This is required because medical science is going to the technology based, which is well connected with the physics, and that is very much connected with the medical sciences in any discipline you want to establish. So this is my request to all the PUC students who are listening, either YouTube or here directly for that. Sir, thank you very much for this one. And I just have one curiosity. Can this attosecond technology, this understanding and this Nobel Prize, will it little enlighten to get certain detection without the invasive process? We often feel the disturbances in the case of the pediatric patient who are actually not acceptable, and the parents never give a permission to invasive methodology to diagnose, or invasive methodology to remove certain clots and remove certain factors which can be cured. I feel maybe laser can be used in that way. Whether this attosecond, this technology by electrons, can it be make in that way?
That is something yet to be seen, because as of now, I am not aware of people discussing the medical applications of attosecond pulses. So the mostly people are talking about its applications in quantum mechanics and looking at the motions of electrons, and how can we chart out in the time domain, how do we really understand these phenomena better. So as you have rightly said, lasers have lots and lots of applications in medicine, and from even from eye surgery, and of course then many other kind of treatments. Yeah, kidney stones and all that.
Yes, that is again used.
Yeah. So the attosecond pulses, for one thing, right now they don't have sufficient energy for doing many of the surgical processes. And surgical lasers are of course extremely well controlled systems. They are much more controlled than our academic lasers or industrial lasers, just because you have to work with human beings, so therefore, so that's a completely different. But anyway, as of now, attosecond pulses, I did not see any paper, or I haven't heard any discussion of using. But who knows? Maybe after a while, yeah. That we have to wait, and probably some application will. So that we have to see.
Thank you. And another this thing that I'm curious that whether you are taking up this issue in your laboratory beside your own subject domain and specialty.
Well, what we have actually, when I joined Raman Research Institute about 23 years back, I joined in year 2000. So we began ultra-fast investigations at that time in the institute. So I developed the nonlinear optics laboratory here. There was nobody working in nonlinear optics, so I was hired actually for that purpose only.
Yes.
So then we developed the laboratory. So we bought the femtosecond laser. We have a 100 femtosecond system here, and we have made a lot of studies in the time domain using that. So, the transient absorption phenomena and nonlinear optical phenomena we have studied. Now, the situation in India as of now is that there is hardly anybody who is really into the attosecond domain doing experiments with real attosecond isolated pulses. So I'm sure that we will get into this area also. So new hires, because the Nobel Prize has been awarded, and I would say that we have been a little bit late. We have been a bit late to get into this area. One problem could be that the equipment that we need is extremely costly. So this is not usually affordable by universities, for example, even for research institutes, because setting up a full-fledged attosecond facility can cost something like rupees 5 crores in Indian rupees. So therefore, this is a deterrent. First of all, you have to raise that kind of money, and you have to get this money normally from the government. So it is not a very easy thing. But anyway, even we are thinking about this, like in the institute also. So the next step, we have to certainly get into this, because that's the only way the country develops. Because
yes, that is important.
So this is very important. So there is no question about whether we should do it or not. We have to do it. So we will do it. How we will do? So we in RRI, we are actually seriously thinking of hiring people in this area. So so we will certainly have a lab. I'm very optimistic that within the next 2 or 3 years, in RRI, we are very likely to have a lab that actually works with the attosecond laser pulses. So that is my hope.
Thank you very much, and wish you all the best for that and your institution also. And looking forward to see that in future and get the news that you have developed and your institution has established, and that will definitely make the different domain, and you can make a multidisciplinary approach with the various expert from the different field to make a practical applications.
Certainly,
thank
sir.
you very much.
Thank you so much. Thanks a lot.
Thank you so much.
Thank you very much, Professor Kajwal Das sir, for your excellent comments. So we have with us Dr. Abhishek. Yes, Dr. Abhishek is a physicist. Abhishek.
Hello, sir. Very good evening, sir.
Good evening. Over to you for your comments.
Thank you, sir. Thank you, sir. Thank you, Professor. Really, it was an informative talk. Actually, I have one question, sir.
Please.
Sir, you have mentioned about attosecond light sources like HHG, right? High harmonic.
Yeah, high harmonic.
Also, you have talked about one more method, sir. That's I think cascading Raman scattering, right, sir?
Yeah. Later Raman
Can you
scattering.
please brief it about cascading Raman effect scattering, how it can be useful in order to as a light sources for this attosecond science?
Yeah, this is again basically in Raman scattering. Cascaded Raman scattering means you generate one Raman line. Okay, that Raman line generates
Yes.
its own Raman line. So
Okay.
for this to normally, if see in the normal case, we use low power lasers for Raman spectroscopy.
Yes, sir.
In Raman's time,
sir.
this was mercury lamps and all that, you know, and the Raman
Yes.
signals were very, very small. I mean, very weak.
Yes, sir.
But
Yes, sir.
after lasers were invented, we have laser Raman spectroscopy now. So nowadays, everybody uses a reasonably low power laser for Raman spectroscopy. So that will
Yes.
generate only, you know, a few Stokes lines and anti-Stokes lines. However,
Yes, sir.
in the nonlinear optical domain, if we use very high power lasers for generating Raman, then what we get is something called stimulated Raman scattering. So in stimulated Raman scattering, the Raman line comes out like another laser beam. It is very powerful actually. It comes out like very similar to another. There are Raman lasers like this. So, you know, the Raman line, which is normally very weak, comes out as a very, very strong beam. And then that Raman line can generate its own Raman. So that is another wavelength. That can generate another wavelength. So then you will have a large number of such wavelengths in the system. So therefore, it is equivalent to having, you know, a much larger bandwidth in the emission, which is a prerequisite for generating any short pulse. So this is why people actually tried using, you know, stimulated Raman scattering for generating attosecond pulses. However, we normally see that it did not pick up so much. What picked up, the technology that picked up is high harmonic generation, more than stimulated Raman scattering.
Okay, okay. Thank you very much, sir. Sir, one more request at the same time. Actually, your complete session was really informative, but most of the PU students and degree students wants to know about this kind of research which is going on nowadays throughout across the globe. And also it is one of the advanced quantum mechanical phenomena. When we want to reach this kind of topic to the common students like the BSc students, MSc students, they are all interested to know about this kind of topic, sir. But the approach when we are teaching and explaining this concepts to that level, definitely teachers community are going to face some difficulties. So I personally, I request you to prepare a small article on it where we can easily make this topic to reach all students level. So it will be definitely useful and informative, sir.
It is coming in current science.
Yes. Okay. Oh,
So,
that's
you
great,
know,
sir. Okay, sir.
You know, the academy actually approached me and I was supposed to give them the article last week, but because of many other commitments, I could not do it. So in the second issue of Current Science this month, November, so I have promised to give the, I'm actually writing it up. So I will give them the article.
Oh, great, sir. Thank you very much, sir.
So
thank you very much, sir. Thank you.
Yeah. Also, let me tell you, there is an article in Scientific American. Okay. It is accessible. You can download that from the net in Scientific American. A good, I mean, it's very simple, you know, very layman kind of article, but it's a good starting point, I would say, for anybody who wants to. Yeah. So the students can certainly.
Also, you have mentioned some research institutes are doing the research on this particular topic. Is there any institution in India are working on attosecond science, including our Raman Research Institute?
In RRI, we will get into attosecond in the near future. So that is our plan. Until now, we are limited to femtoseconds. Yeah, we have femtosecond systems. So when we bought femtosecond lasers, we were one of the first in the country itself. So attosecond, there are 2-3 people, but nobody has really reached a level where you have an attosecond laser in the lab. That hasn't happened. Yeah.
Okay, great, sir. Thank you very much, sir. Thank you very much.
Thanks a lot.
Thank you, Dr. Abhishek, for your presence in the webinar. Thank you. Sir, again, we are very grateful to you for your very, very informative and scholastic talk. On behalf of KSTA and all the participants, I'm immensely thankful to you. I'm also thankful to Professor Kushal Das, sir, and also Dr. Abhishek for joining this webinar, and all the participants who have been with us since 3 days. On 8th, we had a talk on chemistry. Then we had a talk on medicine and economics on 10th. And today we have talk on physics. So all the 4 talks were very, very informative. I'm sure students and teaching faculty will be very highly benefited by these talks. Once again, thank you, sir. KSTA is quite near to RRI. We organize many programs physically. We have started organizing. We'll be inviting you. In fact, if you can remember, you had come once to deliver a talk
Yes.
to KSTA.
Yes, I did. Yeah, I remember. Yeah.
Thank you very much.
Thank you so much, sir. Yeah, thank you so much. Thanks a lot. Thank you. Yeah. Bye.